So my presentation will be a talk about fractal geometry and the application to construct 3D designs. So I will start with something rather simple in fractal geometry. I will use the terminology of contour, for example, the third middle set, also the Foncker curve. I will use also the Sierpinski garbet to define the concept with the dimension of Hausdorff and Bezikovic. And I will show you some examples of what we did using tools of fractal geometry to construct a new 3D design. I will start, of course, with a 2D design. And I will take you, for example, a chessboard. So I will show you right now the image. I hope, Emilie, that the image is okay. Yes, so I can share it. Yes, I think it's good. Voilà. So what we have a new kind of chessboard. This is the chessboard Serre. We call it like this because it's Sierpinski, Einstein, Rosen. You can see that we have white and black squares, but also blue one. You see the dimension of the pattern is in fact 8 by 9 by 9, but of course 3 by 3 with big squares. In fact, is a modification of the Sierpinski gasket to do what? To play chess with a quite different way. So the design was made, in fact, by fractal geometry. And I can show you, of course, a real one to see the difference with the normal and the classical chessboard. So this is the result at the end of the process. And in fact, when you are on the blue squares, you can make a hyper move, which is the following, like the knight move. From here, you can go there. So this concept, I can show you another one here. Maybe it's more easy to see it and to understand the situation. So you see that we have 9 pieces, 9 pawns, but we have 2 queens. So it's quite different. Okay, the other pieces are the classical pieces. The moves are the classical, except for the blue cases. So we use what? We use self-similarity, a fundamental relation due to also Weierstrass and of course Julia and Fatou for the French mathematician. It was emphasized by Mandelbrot, and at the end of the process we use it to define this kind of new chessboard. We generalize this chessboard. I will show you another one and see the other moves. So this is a Serre fortress chess, a little bit more complex with 4 fortresses. The design was used in the 19th century, but we change it and we use this mathematical process to generalize the moves of the blue squares. And now you can see how it is possible to use it. And I think maybe it's more easily understood that we have a fractal geometry. So I will use maybe to show the real one to understand for the chess player, especially. So this is a real one, as we have the design. So it seems to be a design in 2D. In fact, it's in 3D. But okay, I will explain in another example. So the other one was in the field of chemistry. So I will not explain the chemistry process. It's about catalysis, but I will show you the different position and the different situation. At the first time, we have a principle like this, rather simple. So we need something more complex, and that's why we try to find other system. I will show you the first, and you will understood everything. Why? You see Fonkoch here. So this is a geometry like Fonkoch inside, Vauban outside. This is a generalization of this kind of object with only a star and the Fonkoch, the easy one. So we want to use this kind of 3D design to have a maximal surface for a minimal volume. And with this kind of process, we can find another one, this one. So you can see that the design is quite different. And we have already something which is very simple, linear here. Here we have something which is like a networks. And we use, in fact, this L, and we can generalize it at this level with trimenos. So we showed this, and now a bigger generalization, more fractals if you want, with self-similarity. So we have many pieces like cross. Here we have Fonkoch with a star, easy star. So the first level of Fonkoch. Here we have the third level of Fonkoch. So what does it mean? It means that we have a very big surface for a small volume. It's very important when you use gas in catalysis. So with this kind of object, we have made a patent. So I will show you now the real patent. Maybe you can see it right now. So you see the designs. The patent was made with the geometry of fractal sets. It was created to make a system more efficient as a process. So we use, in fact, the Vauban process for the robustness. We use the Fonkoch process for the fractal aspect. And we get a result, which is a patent for the world. Here you can see the first time the patent for France. And we can see here what we use to do with this system. And by this, in fact, we have a process. Now I will explain it with maybe a board. So again, I think you can see it right now. I will write now. Okay. So Cantor, Fonkoch. At the end of the process, we have self-similarity. We want to use it also with Sierpinski. I mentioned already the system of Mandelbrot and also Bezikovic for the dimension aspect. So we want what? A volume, small. We want a surface, big. We want all this kind of thing. The solution is the fractal geometry. And we use it to create 3D design. not only for the design, but as you see it, also for chess, for example, but also for chemistry. And this was the result, 5 patents. So why we use this? In fact, it's more efficient. And this is a paradox because we start with the beauty of fractals. With the fractal geometry, we discover that we can get a nice property, efficiency, and we have also robustness. And with that, we can have an application. And this application is relevant in catalysis. So something which is only about beauty, so from essence, at the end of the process is something which is useful. So we have, something which is related to art, but at the end, we have something which is related to society. This path was made by maths. So if you have now, in fact, the big picture, at the first time we had a problem, a real problem. We decide to put this problem in mathematics. So theory. In this level, we choose beauty first. With beauty, we got truth. And with that, we get the efficiency and the robustness. So at the end of the process, when we are speaking with chemistry level, we see that something which is just a tool for chemistry was in fact a model in math, chemistry, but the relation between the model in maths and the tool in chemistry was made with the 3 design using fractal geometry. So I think we have a very good example of what we can do with the geometry vision using fractal geometry with this kind of concept. To discover new fields of application. And in these fields, we need some tasks. But at the end of the process, we can get a beautiful result about this task with the properties of the fractal geometry itself. So we don't need anything more. The idea is just that if you start with something which is beautiful in math, it can be useful for society. So we have a paradox society needs something for society which is useful. But if you stay at this level and you see only the useful aspect of the process, this will be easy. And we need something which is more complex, because in fact, it's simple. So I try to define something which is very important for us. Easy and simple are different. So in fact, simple is more related to complex, because it's very complex to be simple, and it's very simple to be easy. But complex is not necessarily related with difficult. So the example we gave show that if you stay only in the field of the chess or only in the field of chemistry, you have only a classical approach with no innovation. Now, if you use math in another way, I mean, for example, beauty of fractals, you will find free models which are able to be tools. And you will get an application which is innovative. That's why I want to mention these two examples for you. And I think it's relevant to the conference. And I mean that if we can do this, and at the end of the process, get patents at the European level and also the international level, we have to think that this project was a 3-year project, more than 1 million as a budget, but at the end of the process, the best result was just the application of the beauty of geometry, and for this example, especially the geometry in the fractals set. So the discovery of Mandelbrot, and that's why we are very happy to show this example, because very often, even for the professor, the teachers, or the students, we think that we have to be only in one field. So it was a great pleasure for me to have this presentation in your conference, because I think it's very important to see that we have to be an open mind people to discover new application in new fields, and not just stay in the core of our knowledge. So the first time, what is difficult is in fact the lexic. We have to speak about this concept to other persons, but at the end of the process is very useful, because it's a nice way to go to transdisciplinarity and to get really innovative results. That's all. Thank you so much. Have a good continuation. Thanks again, Emilie. Merci à tous. Ευχαριστώ πολύ σε όλους. Να είστε καλά.